This is a question about the JWST telescope that will uncover some fascinating physics about star formation. When a star is born here, it will actually carve out a sphere. We're given the radius of one of those ionized regions. We have some information about the star that is causing this, and we're given that its temperature is 35,800 Kelvin. We also have the surface temperature of the sun and its peak wavelength. So my plan for this question is to use Wien's law. Now this says that the surface temperature of a star multiplied by the predominant wavelength, call that lambda max, will be a constant. Now that in turn means that T1, let's just call it lambda 1, will be equal to T2 lambda 2. Rearranging this for lambda 2, we're going to get that this here will be equal to T1 lambda 1, divide that by T2. Okay, so the surface temperature of the sun is just 5780, multiplied by the peak wavelength, which is around 500 nanometers, times 10 to the power minus 9. Divide that by the effective surface temperature that we're given, which is around 35,800. And we're going to get a pretty small wavelength of around 8.07 times 10 to the power of minus 8 meters. Now this is looking pretty promising so far, because the smaller the wavelength, the higher the energy. So let's calculate the energy and see if it's ionizing. And this here will give me around 2.46 times 10 to the power of minus 18. We're going to need to convert this to electron volts to determine whether this is ionizing or not. And if it's greater than 13.6, it will be ionizing. So the way we would convert that is just literally by dividing by the electron charge, giving us around 15.4 electron volts, which is higher than the 13.6 electron volts needed for this to be ionizing, and the first part is done. Okay, for the next part, we're given NH, which was the density of hydrogen, is around 10 to the power of 9, and ionization will lead to an equilibrium temperature inside the sphere. Okay, we're given some more data. Assuming that the star emits monochromatically, that means just the same wavelength, at just that exact peak ionizing wavelength, estimate N, and hence estimate Rs. Okay, well, let's have a look at what N was. Scrolling back for the problem, we can see that N is the number of ionizing photons per second. Now here's a little exam tip. Anytime you see ionizing photons or photons per second, then we'll probably have to use the power. We're actually given the luminosity of the star, because that's just around 1.47 times 10 to the 5 times the luminosity of the sun. The number of photons will be equal to the total energy, which is the luminosity of the star in this case. Divide that by the energy of each individual photon. So let's just leave that not in electron volts. And what I'm going to do is I'm going to plug that number there. Okay, so the luminosity was 1.47 times 10 to the power of 5 multiplied by the luminosity of the sun, which is also luckily given, 3.85 multiplied by 10 to the power of 26. Divide that by 2.46 times 10 to the power of minus 18. That's going to be a large number with a lot of photons. And this here will give me a gigantic number of 2.30 times 10 to the power of 49 photons per second. We can see why all of these ionizing photons can carve out a sphere in a nebula. Okay, so with that number, we can plug that in here. This was given in the question, this was given in the question. We know what 3 is, we know what 4 pi is, so we're in business and we can just calculate the radius of this ionizing bubble. And this here will give me around 2.61 up to 3 significant figures times 10 to the power of 16 meters. Now they would like us us to give this answer in light years, so all I'd need to do is just divide that by the number of meters in a light year. So I'm going to take that number, 2.61 times 10 to the power of 16. Then I'm going to divide by 9.46 times 10 to the power of 15. Which is the amount of light years in meters, typically given in most exam formula booklets, but if not, you could really easily calculate that as well. Giving me around 2.76 light years. So the bubble within the pillar has a radius of 2.76 light years. Okay, part 3, the height of the pillar on the left is 5 light years, so the whole thing is around 5 light years. How many such large stars will be needed to photoevaporate the pillar given long enough such that it's no longer visible? Okay, well, because the radius is this, well, this is not drawn up to scale. One of these is going to have a radius around 2.76. So in theory, just one of these should be totally enough. So I am going to go for part 3, just 1 star. If you wanted to be absolutely sure, maybe we'll get 2 of them. Let's have a look at this cool equation for part B. This part is really cool. The star will not just carve out its surroundings by exerting pressure, but that pressure can also trigger further collapses of further stars in the region. We're given an equation for the mass that will collapse under pressure, and we are given an expression for the radiation pressure that the star actually exerts. Okay, so what we need to do for part B is to calculate the cloud mass that will begin to collapse just outside of the ionizing bubble to form a new star cluster. So my plan is to calculate the radiation pressure first of all by plugging in this RS value. Then we're going to take this, I'm going to plug this into this formula. So the luminosity, let's see, what was it? Around 1.47 times 10 to the power of 5 solar luminosities, and the solar luminosity was 3.85 times 10 to the power of 26. Now we're going to divide this by 4 pi times the radius squared, which in meters was 2.61 times 10 to the power of 16. Don't forget the square multiplied by the speed of light, 3.0 times 10 to the power of 8. And this here will give me a pretty tiny number, 2.20 times 10 to the power of minus 11 pascals. But remember, this is pressure from light, so I'm not yet expecting a very large number. Okay, well, let's calculate the mass that's about to collapse. So I'm going to call it m subscript c, and this here will be equal to 1.18 times Boltzmann's constant, which was 1.38 times 10 to the power of minus 23. Square that. The temperature is squared, and then we're going to be dividing by the pressure, which is just this number here, raised to the power of half. This is essentially just square rooted. Let's just write it as a square root. So this here will be 2.2 times 10 to the power of minus 11 multiplied by g raised to the 3 halves, which was 6.67 times 10 to the power of minus 11. Carefully writing these out, very easy to make a mistake. Multiplied by the mass of hydrogen. We're not given the mass of hydrogen per se, but we're given the mass of a proton in the formula booklet, which is good enough. So 1.673 times 10 to the power of minus 27 kg, and then all of this is squared. Quick check of all the powers: square, square, square root, 3 halves, and then squared. Time to put this into a calculator. And if we do that correctly, we're going to get around around 7.855, let's call it 7.86 times 10 to the power of 30 kg. Now let's take this number and then divide it by the solar mass, so 7.86 times 10 to the power of 30, divided by the mass of the sun, which is around 1.99 times 10 to the power of 30, and let's see what we get. And that's going to give us around 3.95 solar masses. How amazing is that? So that big star, the center of the cluster, will actually be collapsing mass, which is equivalent to 3.95 solar masses just outside of an ionized bubble of radiation. Amazing problem. In the next part, we're given two amazing expressions, one for the gravitational pressure, which is trying to collapse the star, and one for the outwards exerted pressure from the radiation and the gas pressure. Examining this on the surface, this appears to be a little bit complicated, but in reality, we're given this in the question, we know what the constants are, we're given the temperature, and we can calculate the average mass of the particles relatively easily. So for part one, estimate the pressure of the center of the sun. How amazing is this question? Okay, so we can calculate the value of the average mass of the particles by 2 over 1 plus, let's see, we're given that x is equal to 0.35 plus 0.5 times y, which is 0.65. So this means that the average mass will just be equal to this expression. I'm just going to write it like that, multiply by the mass of hydrogen, which is 1.673 times 10 to the power of minus 27. Let's put that in a calculator. Okay, this here will give me around 1.408, let's call it 1.41 times 10 to the power of minus 27 kilograms. So now we're ready to take this and plug this into this expression to work out the total pressure. And after so much substitution, I have around 2.352, let's call it 2.35 times 10 to the power of 16 pascals, which is an enormous pressure. Next part of the question is asking us to calculate the radiation pressure as a percentage of the total pressure that we've just calculated. So this will essentially be this number divided by that number, i.e. just this part of the expression, divide that by 2.35 times 10 to the power of 16. This here will give me around 6.5 times 10 to the power of minus 4. We want that as a percentage though, so I'm just going to multiply this by 100, and this here will just give me around 6.5%. For the next part of the question, we're going to see what is actually opposing this pressure, and that is the gravitational pressure, and we're going to compare it to the total outward radiation pressure. So this integral, the question says, is normally really difficult to carry out. Okay, so we're given that the density is actually a constant, so what I'm going to do is I'm going to express this integral from 0 to r in terms of the density. Now g is just a constant, that's fine. Mass is just equal to the density multiplied by the volume, multiplied by the density again, divide that by r squared, and then integrate with respect to the r. So this thing here will then be equal to g. The density is a constant, so I can just take the factor of the density squared just outside of the integral, and the volume is just going to be 4/3 pi multiplied by r cubed, divide that by r squared dr. And this is just equal to g density squared 4/3 pi. Disintegrated from 0 to rs will just give me rs squared divided by 2. Let's plug in some numbers. Okay, to evaluate this integral, we know what g is, we know what pi and 4/3 is. We're given the radius of the white dwarf, which would be the radius of the Earth. We need to evaluate its density though. Should we just do that across here? So the density of this white dwarf star will be given by its mass divided by the volume. So we're going to have the mass of the sun, which is around 1.99 times 10 to the power of 30. Let's divide that by the volume, which is going to be 4/3 pi, the radius of the Earth, which is 6370 times 10 to the power of 3. And all of this is cubed. If we put this into a calculator, we're going to get around 1.8 times 10, let's see to what power, times 10 to the power of 9 kilograms per meter cubed. And now I can plug this back into this integral. So the gravitational pressure will be given by G, which is 6.67 times 10 to the power of minus 11, multiplied by the density squared, which was this number, 1.8 times 10 to the power of 9, all of it squared, 4/3 pi multiplied by the radius, don't forget the square, 6370 times 10 to the power of 3 squared, divide that by 2. Calculating this, we're going to get an answer of around 1.83 times 10 to the power of 22 pascals for the gravitational radiation pressure inside of a star. And now let's calculate how many times larger it is compared to the outward pressure. So I'm just going to divide those two numbers, 1.83 times 10 to the power of 22, divide that by the radiation pressure, which we calculated a long time ago, 2.35 times 10 to the power of 16. That's going to give me around 7.8 times 10 to the power of 5. So it's nearly 1 million times stronger, the gravitational pressure inside of the star. The next part of the question is really fascinating. The photons that are created inside of the surface of the sun, right at the center, actually take a lot of time to reach the surface. But just how long and why? Well, they're continuously reabsorbed and re-emitted, reabsorbed and re-emitted, reabsorbed and re-emitted, and they eventually reach the surface. We're given the energy density of the sun, and using the luminosity, we can work out that time. Well, why is that? Because we know the total energy will be given by this density times the volume. So it'll be 4 times Stefan's constant, t to the power of 4, multiplied by the volume of a sphere, which is 4/3 pi times the radius of the sun that's actually cubed. Now that we have this energy, we can then use the fact that energy is power times time. But remember, power is just exactly the same as luminosity. So all we need to do to work out the time is to divide the energy by the luminosity. Well, let's first calculate the energy. Okay, this will give me a total energy of around 5.34 times 10 to the power of 38 joules, which is enormous. And as we said, the time t will be given by the energy divided by the luminosity. Let's just do that right here. So that's energy over power. 5.34 times 10 to the power of 38. And in the previous part of the question, we're given the luminosity, which was 3.85 times 10 to the power of 26. Okay, this here will give me around 1.387 times 10 to the power of 12 seconds. Let's convert that to years. And this here will give me around 43,981 years. Let's call it 44,000 years. So it actually takes 44,000 years for a photon to go from the center all the way to the surface. How incredible is that? Well, we know that light travels at the speed of light, so what's actually stopping it? Well, it's being continuously absorbed and re-emitted, continuously reabsorbed and re-emitted. And we're given this equation that D is equal to L delta N. Well, how are we going to find the mean free path for how long the photon travels between absorption? This is actually a really tricky part of the question, and in order to tackle this, we must realize a couple of things. Number one, the total time that we've just calculated will be given by the number of steps times the time length of each individual step. But additionally, the time of each individual step will be given by what is known as the mean free path. In other words, that distance here of each individual one, not drawn up to scale, of course, but this here will be L. So let's see, time is going to be distance divided by speed divided by the speed of light. Okay, well, this means that T will be N L over C, meaning that N will just be given by T multiplied by C, and then divide that by L. That's right, isn't it? Yep. But we also know that this is also true. The total displacement is equal to the mean free path. This is just a random walk equation, which has been nicely given to us, multiplied by the square root of N. The total displacement from here to here, this is actually D, will just be equal to the radius of the sun, and that's going to be equal to L times the square root. Now, rather than N, I'm going to write TC over L, and okay, let's tidy this up. So this here will be given by the square, L divided by square root of L will just give me the square root of L TC. So we're going to have R sun squared is going to equal to L TC. In other words, L will be R sun squared, divide that by TC. Okay, we were given the radius of the sun, which was just here, 6.96 times 10 to the power of 8. And let's square that, divide that by the time that we found here, which was 1.387 times 10 to the power of 12. Multiply that by the speed of light, called 3.0 times 10 to the power of 8. Let's see what we're going to get, giving us a grand total of 1.16 times 10 to the power of minus 3 meters, or around 1.16 millimeters as the total distance between continuous absorptions. Okay, now that we have L, we can work out what N is pretty easily. So remember, let's just square everything. D squared will be L squared times N. In other words, N will be D squared divided by L squared. D was just the radius of the sun, so it'll be 6.96 times 10 to the power of 8, divide that by L, which was 1.16 times 10 to the power of minus 3. Don't forget to square everything, giving me around 3.6 times 10 to the power of 23. Okay, final part of this question is about neutrinos. The neutrinos hardly interact with matter, which means that we can learn a lot about the sun over time by studying them. So each neutrino actually corresponds to an energy of around 13.1 mega electron volts, and the ones detected from the Earth are responsible for 92% of the sun's energy output. We're also given the flux of neutrinos on Earth, which is a pretty large number per square centimeter. Well, let's work out 92% of the solar luminosity. So I'm going to do 0.92 multiplied by the luminosity of the sun, which was given here 3.85 multiplied by 10 to the power of 26. Now what I want to do is work out the total number of neutrinos that are actually produced. So I'm going to divide that number by 13.1 mega electron volts. So this here will be times 10 to the power of 6, and each individual electron volt will be 1.6 times 10 to the power of minus 19 joules. This here will give me a huge number of neutrinos. 1.6898885, that's enough digits, times 10 to the power of 38 neutrinos. Now, how much of them do we expect to be on Earth? Well, I'm just going to use the fact that intensity is given by the power divided by the surface area. So I am going to take that number, 1.6898885 times 10 to the power of 38, divide that by the surface area of a sphere, exactly identical to the power drop of a light bulb. It will essentially spread like a surface around it, like so, and we can use intensity as power over area at any point on this surface. Okay, so the surface area of a sphere will just be 4 pi r squared. R in this case will just be the astronomical distance, the distance between the surface of the Sun and the Earth, the average distance, which was 1.5 times 10 to the power of 11, and then we're going to be squaring that. And this here will give me around 5.97 times 10 to the power of 14 neutrinos per square meter. To convert that to centimeter squared, I need to divide by centi squared, which is 10 to the power of minus 2 squared. So this is 5.97 times 10 to the power of 10 neutrinos per square centimeter. Now this is extremely close to this value that we have across here. In fact, it would probably be even closer if we had a more accurate value for the astronomical distance, for instance. The percentage difference between them is very small, which means that the fluctuations of energy production of the Sun over the last 44,000 years have been very little. In fact, the Sun has been very stable. Well done, guys, you have solved the last question of the British Physics Olympiad. Now, if you're preparing for it, you absolutely need to have a look at my next video with some unmissable tips which will help you score even better on the Olympiad. And this video is right over here. Enjoy.